recorder, and now we'll go and get the PowerPoint started. Chapter 19 is where we are now, and we should be current slide, I believe. If not, we'll get there. No, we're somewhere past that. We've already talked about faulting, classes of faults, other faults, whose fault. Okay, here we are on earthquakes, causes of earthquakes. Here's where we are. Locating and measuring earthquakes. That's where we're starting today. So let's get to slideshow from current slide, and we'll go from there. Now, at this point, I've got to move my taskbars around. I know you can't see it, but people who are going to be watching the videos, they would be smack dab covering up materials for those. And I also scoot over Matthew. He's kind of in the way here. Just move you a little bit to the right. There we go. All right, any other questions, issues, concerns that you want to bring up before we get started today? All right. Now, let's just talk about where we are and where we're going. Okay? We're in chapter 19. Last week we finished chapter 18, did the lab for 18, and did the I hope I posted the test for 18 for you, and that should be out there. Okay? We're now in chapter 19, and I'd say we've made reasonably good progress through 19. We're in 19.3, we have 19.4 to go, and we'll be through. So I think in the next 2.5 hours, or whatever we have left of that, we should be able to finish 19. Okay? Which means then we'll move right on in and start chapter 20. I don't think we'll get super far in 20, but we will get started in 20. But at 3:45, we will pause, we will stop, and we will do the lab for chapter 19. Now, I put that out there under week 5 instructional materials. Okay? So if you haven't already done it, it's a lab in 2 parts. The first part is a printout it's a PDF file, and that's what I got out of the lab manual that goes with this course, and it's on latitude and longitude. Now, we're not doing latitude and longitude now, but we have done it in the past. We'll still be referring to it all sorts of times. So that's the lab for this week. Now, the first part of it is fairly short. Oh, here comes somebody coming in. I can't see who it is because Gerald. Okay, so let me let Gerald in while I'm marking Gerald present. Gerald Coleman, there he is. Okay. Now, I can't tell if anyone else is under that window or not. This is the strangest thing. It's something between Zoom and Blackboard. They just don't get along well, it seems like, because when someone's coming into the class, I get a box up here that tells me, but immediately then either Zoom or Blackboard blackens the box because it's saying that, you know, move it, don't have it in this shared space here. Well, when they put that there, I can't see who's coming in. So it's kind of an awkward situation. And that's why I have to check every time I see something happen to make sure that somebody's not coming back into the room or coming in for the first time. Okay, so what we'll do, we'll hopefully finish 19 today. We'll hopefully get started in 20 today. Then at 3:45, we'll start the lab for chapter 19, which is on latitude and longitude, which is stuff we've already talked about before in a couple chapters ago, but we'll take that and run with it. We'll do the part that came in the lab manual, but that's only a certain fairly short lab, and then the rest of them you'll be doing however you choose to do them. What it is, I will give you, and it looks like someone else might be coming in, but I don't see anybody. Let me see. This thing popped up. Nope, nobody else is waiting.
Someone asked, did you say the chapter? What's that
Okay. Um, I said earlier, I think I put the chapter 18. Say again? Okay. Um, okay. Well, the thing is, I've got so many things open, it's hard for me to get to the chat box as well. Okay. See, I've got Screencast-O-Matic open. I've got two PowerPoints open. I've got Zoom open, and um, it seems like there's something else that's here. Oh, whiteboard. Yeah, there's lots of things open, and I can't get to them all without losing something. If I go to something, then something else gets bumped off. So if y'all can let me know when there's someone asking a question like that, what I'd rather is y'all, if you're hearing me, go on and turn on your microphone, unmute yourself and ask the question. Unless it's something very private, and if that's the case, then I'll try to answer that through the chat. But there I have to stop and type it in and stuff like that. So that's why I tend not to do that much chatting. So sorry about that. I'm just a dinosaur, and this stuff is kind of overwhelming to me. So I just don't do that many things. I'm just trying to focus on this. Sorry about that. Okay. So what I was saying is the first part of the lab is part that we'll do together as a group. And then the last part of the lab, I've made an assignment, and this is the second lab you'll see out there. That's the one that is the Word file, the doc file. And that one you'll go in and pick up where you left off with the PDF file, and you will then find, and you can do it any way you want to. You can use the internet, you can use your smartphone, you can use, if you got a syllabus handy, that's not what I meant to say, oh goodness, what do you call them? Atlas. An atlas handy, you can go look it up there. Any way you can, finding, specify a city, not where you live in Alabama, okay, another city in Alabama. Another city in the US, not in Alabama. Something from Canada, something from Europe, something from South America. Find the city and also give me the city and its latitude and longitude. So that's what the rest of the lab will be, and we'll go over that when it gets to be lab time. Okay? Then once we finish the lab, I will put the chapter 18 test out there, 19 test, sorry. This is test number 6. And I'll tell you, this is a different kind of test because the questions they had on the test bank were so abstract, nitpicky, I just didn't like most of them. And I took the ones I did like and I adapted them. I made them some that were multiple choice. There's still a few multiple choice, but I made some fill in the blank and some other things. So it's a one-page test, and basically you'll need your book, I think, and I would suggest that for any of the tests, but you definitely will need the book and that you follow through on what's in the book. So if we were back on campus, all these other tests were going to be in-class tests. You could have a page of notes, formula and equation sheet, whatever you want to write down on a piece of paper, but you do the test in class. This one, because it was so abstract and stuff, what I did, I made it a take-home test. Well, all of your tests are take-home tests now. So here comes Labrina. Let me get her in. So this is one that looks different. It is different. It's the only one like this you'll have this term. It's just a one-page test, and you'll just go from there. So Labrina is here. I guess she can hear us now. Yeah. Now there was another bip there. I don't know what that was about, but I don't see anyone else coming in the class. All right. Then hopefully next time we will, and so after we finish the lab today, or I finish the lab, y'all will probably still be working on it. I will go on and post the 6th test, the chapter 19 test out there probably post it on Blackboard Message, but I may also post it under assessment, week 5 assessment, because there is a place there for it, but sometimes they won't let me post things there. So I always post it on Blackboard Message. If you see it there, I'll change that week 5 assessment to test 6 or chapter 19 test or something like that. So you should be able to pick it up either place then. But again, sometimes they whoever put these templates together left out some things, and I just can't operate with them because they left out too much. Okay. So, any questions, issues, concerns before we get started today? All right, I'll take silence to be negative. So, we're in chapter 19, Building Earth's Surface. We're under 19.3, Earthquakes. We got started in this last time. We're now on page 489, which if you have the small books, that's 19-9, the 9th page in chapter 19. Sort of the bottom of the first column, and it's locating and measuring earthquakes. Now, where do earthquakes occur? If you watch science fiction, you think earthquakes come at the surface and split open and people and cars and things fall into them. That's fiction. It's not even science. That's not what an earthquake is. What an earthquake is something way, way underground, okay, where maybe some of those plates are subducting under other plates or other things are going on. You have transfer boundaries. Something's happening. It could be fairly near the surface, but most of the time they're fairly deep. And somewhere in there, something got hung up and then released suddenly. That's what creates the earthquake. So the focus of the earthquake is the actual origin of the seismic waves. And here's Diana. I think she was already here. She must just be coming back. Yep, I already had her here. Okay. So, the focus is where the earthquake occurs. Generally, somewhere underground, usually very deep underground. The actual origin of those seismic waves. Now, what we talk about all the time and what you'll hear on the news, the epicenter of the earthquake. Okay, here comes Amari. Okay, or at least his iPhone is coming in. So let me get Amari here. There he is. Okay. All right. Where the epicenter is, it's the location. Say the earthquake is down here somewhere. Here's the crust somewhere way up here. The epicenter would be directly above wherever that focus is. That is what we call the epicenter. Now, why do we call it that? That's where the waves first reach the surface. That's the epicenter. My phone's ringing downstairs, but I don't care. They can leave the message. It's been ringing crazy all day long. I think I know part of the reason, but anyway, that's beside the point. Now, let's get a graphic to show what we've been talking about here, but the graphic won't start until I click the screen again. There it is. So here we have a fault plane. Anyone tell me what kind of fault this is? Which is the foot wall, which is the hanging wall? What kind of fault is this? This is a normal fault. The foot wall's on the bottom, the hanging wall's on top. The hanging wall is sliding down the foot wall, or it was sliding down. It got hung up, it got hung up, and then suddenly something gave. So that was where the earthquake occurred. Right there was something was hanging it up there. That's the focus of the earthquake. Now, the seismic waves go in every direction. They go down through the earth, they go to the surface, they go everywhere. Those seismic waves go in all directions. There's P waves and there's S waves. Primary waves and secondary waves. Pressure waves and shear waves, okay, however you want to call them. Longitudinal waves and transverse waves, okay, however you want to call them. Well, those that reach the surface first are right here. That would be the epicenter. That's where we notice what's damaged worse on the surface. That's called the epicenter of the earthquake. Now, I guarantee you the earth doesn't slide down that much at a time. So this is a little bit of a misnomer here. You know, it's just for illustration purposes. Okay, once they get to the surface, then the waves, the seismic waves, have nowhere else to go, so they start moving along the surface like this. That's then what we call the surface waves, and they go like this. They're primary and secondary waves while they're coming through the earth. When they reach the surface, then they go laterally, and those are called the surface waves. Those are the slowest. Okay, so if you were over here somewhere, way over here, you get the P waves coming in first, and you had a seismograph, and then the S waves come in later, and finally these surface waves make their way to you there. That's why they're last. Okay, so that's locating the earthquakes. How do we measure the earthquakes? Well, that's what a seismograph does. Seismo means seismic waves. Graph means basically to plot or to measure. Okay, that's the instrument used to detect and measure earthquakes. And as we've said several times before, and I've just said it again, you have the P waves. That can stand for primary waves. It can stand for pressure waves, which we get from the word compressive waves. Okay, those are all longitudinal waves. They happen to be the fastest waves. They get to the seismograph first. Shortly thereafter, you get the secondary waves, the S waves or the shear waves. Those are transverse waves, and they get there second. And then finally, when the P and S waves reach the surface, they send out a number of surface waves parallel to the surface. They get there last. Okay, these are up and down waves. This is what you feel. Okay, unless you're way underground, then you would feel one of those other waves. Okay, now here's what a seismograph looks like in general. It's firmly fixed on some solid rock, very solid platform, very solid column here, substantial. But here you have a pivot. This pin can pivot back and forth laterally. Here you have a wire that holds it in the same position always. And usually the paper is always rolling, and most of the time you get nothing but a flat line. You may get little bitty tremors that may be caused by, I don't know, airplanes taking off, or I don't know what could cause these tremors. Just little noise, okay? But if an earthquake ever hits, your P waves come in and make the seismograph wiggle. Because the earth moves, the pin is trying to stay still. This heavy weight here is called an inertia block that tries to keep in the same place, but when the table moves, when the earth moves here and goes back and forth, this tries to keep steady, and that's what makes the pin go back and forth like this. The P waves will come in first, then the S waves come in next. We'll see a drawing of this later, and then finally you'll see the surface waves, which is usually the largest of them all. Okay, the ground movement is this way, and that creates the drawing here. Now you have these all over the surface of the earth. I think every country, whether they're whatever their economic system is, their political system, it doesn't matter. Everybody agrees to keep and share the data that come in off their seismographs. That lets everyone know where the earthquakes have occurred, and now we can better understand what to do about them, to help people, whatever, where to send help, whatever. So there's your seismograph, and it's measuring the movement of the earth by that pin. Okay. Now, as I've said a couple of times already, the P waves, the primary waves, travel faster than the secondary waves, the S waves, the shear waves. The difference in their arrival times correlate to the distance from the earthquake. Now, here's a sort of dumb example of this, but hopefully it'll make sense. I don't know where you are right now. I'm just going to assume everyone's in Birmingham. Now, if you're not in Birmingham, just make up other towns. Let's say you're in Birmingham, and there's two of you, okay? And you're going to go to, let's say, first to Tuscaloosa, okay? Now, if you were to leave at the same time, but one of you is going to average 70 miles an hour, and the other one you know is only going to average 60 miles an hour. Say one of you is driving a furniture truck and the other one's taking a car. So you're going to leave at the same time, but one's traveling at 60 miles an hour and one's at 70 miles an hour. Well, guess what? The one that gets to Tuscaloosa first will be the faster one, and let's just say it gets there 10 minutes earlier, okay? Something like that, okay? But let's say maybe you're not stopping at Tuscaloosa. What if you're going on down to Meridian, Mississippi, okay? Well, then the difference in time arrivals in Meridian, if you both keep traveling, one at 70 and one at 60, then the difference in time is going to be further, is going to be longer, because that truck going at 70 or the car going at 70 is going faster for a longer distance, so he's getting further and further ahead of the slow one, okay? Well, that difference in time, difference in arrival time, correlates to how far you travel. Same thing here. The difference in the arrival times between the P waves and the S waves tells you how far away that earthquake was. Now, it doesn't tell you where it was, it just tells you how far those waves traveled. So what you can do, if you are here and you know the P waves got in at a certain time, the S wave got in at some time, and that tells you you were 300 kilometers from that earthquake, that means you could take a circle, a compass 300 kilometers big, you might say, draw that on the map. That earthquake was somewhere on that circle, okay? Well, let's say down in Cuba, say, even though it's a communist country, everything's different there, they're also measuring that earthquake, and they're sharing the data with you. Well, they send back and say it was 200 kilometers from them, so a circle draws around that. Well, that gives you 2 points probably of intersection. You need the third place. So let's say England measured that too, and let's say maybe it was 1,000 kilometers from England. Draw that circle around that place in England, and now where those three circles intersect, that'll only be 1 point or something pretty close to that. That's going to be what we call triangulation. You have to have three sources of information. That's used to pinpoint the epicenter on the surface of the earth, and then you'll start worrying about how deep it was at the focus. So that's what you're measuring, and this shows the same type thing here. This shows from Z, I was calling this Cuba, let's call that 100 kilometers away. Anywhere on that circle, that could have been where the earthquake was. But we say somewhere in Alabama or somewhere is Y, and that was going to be 150 kilometers away from that. Well, that earthquake could have been here or here. Either place would fit. Somewhere else, let's say Missouri, well, that's too far, but let's just say might be 200 kilometers away. Well, 200 kilometers from this one, it could be here or here. 200 from this one could be here or here. But from all three, it's got to be there and there alone. Now, if it doesn't exactly pinpoint The reason may be that it was a pretty deep earthquake and those waves came through the earth this way, not on the surface of the earth. So there's another thing you have to keep in mind. But it is. So the further you are, okay, this is distance from the earthquake. Here's the time of first arrival. Again, I would have put these graphs the other way. Put the time down here, distance up here, because the distance depends on the time. But either way you do it, it'll work. This is the time of first arrival of the P waves would be here, but the S wave didn't get here till then. Well, they're pretty close together. That means it had to be pretty close, okay? But if the P wave arrived at this time, and then the S wave arrived here, that means that's a pretty long distance away. So that could have been the 150 kilometer here. Down here may have been the 100 kilometer. This is in a different location. Up here could have been the 200 kilometer distance from the earthquake. The difference between the arrival times of the P and S waves, that lets you know how far you were from the focus and or the epicenter. Okay. Now, you have to have 3. Same thing is true of GPS. If you go out with your car, anything else, and you're wanting to find out exactly where you are, you've got to have 3 signals. If you don't receive 3 signals, it doesn't know where you are. It knows if you only got 2 signals, you could be here or you could be there. It doesn't know where. It's got to have at least 3 signals. May get more than 3, and then it can maybe pinpoint a little bit better if there is some sloppiness in those first 3. All right, any questions? That's what triangulation means, and that's why we have these seismographs scattered all over every country in the earth. Now, I don't know how many are in the U.S. I'm sure there's some in California. I'm pretty sure there's some in Nevada. I bet you there's some here in the Southeast somewhere. I just can't say what state. Maybe every state has them. I don't know. But there's a lot of them out there. They share the data, and then they can pinpoint where those earthquakes are. Maybe a computer program doing that for them, but it can be done. All right. Well, how do we classify earthquakes? Okay. Well, this is on page 490. So it might need to turn a page from where you were. By the way, there was a pretty good illustration here, and I'm going to show it to you. It wasn't on the PowerPoint, but here, let me show you here. This is showing the actual seismic waves coming from the earthquake here to your location over there. The P waves get there a little ahead of the S waves. They go through the earth. The surface waves, of course, have to make it all the way to the surface and then head out that way. So that's why they're the slowest to get to you. Now here is a good graphic of what you see. You see the P waves happening first, then comes the S waves. They actually tend to be a little larger than P waves, but you can really tell the difference in the first and second. That time difference that you received those, that lets you know how far you are from the earthquake. Literally it's from the focus, pretty close to that, but not too bad from the epicenter as well. And then your surface waves come last. They really shake and rattle and roll, but they're coming over the surface. They're the slowest, and they probably have the greatest error in them. The P and S waves probably are pretty consistent. Okay, so that graphic there, if you got your book, you can tell it. There's another one: P waves, S waves, and surface waves. S stands for secondary shear waves. The surface waves, of course, stand for those that are on the surface. Okay. Now, we're going to talk about classification of earthquakes, then we're going to come back and look at a couple of examples. These are worth looking at. Most of the time I skip on over this or just give them a wave or something. But these are pretty much what we've just been talking about. But let's first talk about how you classify the earthquakes. One is, how deep is that focus below the epicenter? Okay? You classify it three ways. Shallow focus earthquakes. Now they're down to about 70 kilometers deep. And by the way, that's about 42 miles deep. My goodness. That's called shallow, but about 85% of all earthquakes occur in that shallow, and that would usually be in the lithosphere. It may be just in the crust. The odds are it's somewhere in the lithosphere, which is the crust and the upper part of the mantle. Okay, 85% of earthquakes there. The surface rocks are more brittle because they're colder. There's more plate friction near the surface. Okay, as you go down deeper, things get hotter. Things, when they heat up, they sort of go past each other a little more easily because they're now beginning to be sort of semi-liquid or something. But when they're all solid brittle rocks, that's where 85% of the earthquakes are in that first 42 miles deep. Then you have the intermediate focus earthquakes. Now this is a typo here. If you look in your book, you'll see that should be 350 kilometers deep. So I'm going to get my pen if I can find it. There it is. My ionizing pen, and try to correct that for you. Probably should change it to blue. I don't think I can. Let me see. Where is... I can't find the pen. Oh, maybe it's not going right. On my other PowerPoints I can write. I can't write on this one. Oh, I'm using the wrong end of the pen, no wonder. Here we go. This is 350 kilometers deep. Now what is 350 kilometers? It's pretty deep, I'll tell you that. Oh, wait. It's about 210 miles deep. You call that intermediate focus? Yeah, that's what it is. About 250 miles down. So between 42, 45 miles and 210 miles, that's called the intermediate focus earthquake. Now you're definitely in the upper part of the mantle. So most of these were probably within the crust. Probably within the crust. The crust rocks are more brittle. There's more plate friction in the crust. This is in the upper part of the mantle, and this is your intermediate focus quakes. Now they don't give you what percentage, but we can figure that out. This is between 210 miles down and 420 miles down. These are the deep focus earthquakes. This is in the lower part of the upper mantle. Remember, we did this before. The upper mantle is that above the asthenosphere. This is all part of the lithosphere here. And you're down near that asthenosphere in the lower part. And when I say near, I mean you got 120 miles to play in and call it near, you know. This is only about 3% of the earthquakes. So if 85% of them are shallow, 3% are deep focus earthquakes, that would leave you, anyone do the math? 12%. About 12% are intermediate focus earthquake. So the vast majority of your earthquakes are going to be up here within the crust where everything is sort of brittle, and that's where you're going to have those things hanging up and then suddenly releasing and letting go. So most of your earthquakes will be shallow focus earthquakes within the top 42 miles or so. Excuse me. I've been talking since 8:30 this morning, just about nonstop. Okay. My throat's not all with me here. Okay, so that's how we classify the earthquakes. Now, before we get into measuring the earthquake strength, let's look at the examples that they give here in the text. I hope you got your books open, but if you don't, these are worth looking at. Now this is, again, they sort of stretch to make these examples here in the text, especially in the part we are. The first part of the book, physics and chemistry, you're doing all kinds of examples all the time. But in earth sciences and astronomy, that kind of stuff, there's just not that many things to solve. So they sort of make up things. And this is sort of a made up, and it kind of, in a sense, is a little on the ridiculous side. It's realistic, but it's just not a very good question. Which station is closer to the epicenter if one seismic station in Nevada receives the P waves at 4:30:15 a.m. and the S waves at 4:30:35 a.m.? So only 20 seconds later. While a different seismic station in California receives the P waves at 4:29:59 a.m. and the S waves at 4:30:15 a.m. Well, number one, the one that got them first is the closest. I mean, that's pretty obvious. So the one in California got it at 4:29:59. The one in Nevada got it at 4:30. Obviously, the one in California was closer. So that was a really silly question almost, but what they're trying to do is get you to see how much time it took. Well, what was the time? We already said 20 seconds between the P waves and S waves in Nevada. In California, it was only 16 seconds. So there again, that shows that the California was closer. Okay? So it's pretty obvious there which it is. So let's look at example 19.4. At what time does a seismic station receive the S waves if the P waves arrive at 11:51:51 and the S waves arrive 75 seconds later? Well, that has nothing to do with seismic waves. All that's doing is saying, can you add 51 seconds to 75 seconds? Well, of course you can. Well, wait, first let's call 75 seconds 1 minute and 15 seconds, because that's what it is. 1 minute is 60 seconds. So let's add 51:51 to 1:15. So that would be 53:06. What does that have to do with the waves? Really nothing. It's just getting you adding seconds, minutes, and hours. Seconds and minutes is all it was. So again, a little bit of a silly illustration, but not completely unworthy, but it's just a little bit on the crazy side that they would even bring that up. All right, so let's move on to measuring earthquake strength. This is on page 491, just like those examples were. Okay, measuring earthquake strength. Now, they've had several systems over the years. Okay, early on, they measured earthquake strength by how much damage they did. Basically, what are the effects of the earthquake? What kind of structural damage do you do to buildings? How many fires are lit? What kind of landslides do you see? Do you actually see displacement of land surfaces? Do you actually get a tsunami coming out of it if it was near the water? Okay, these would all be effects of the earthquake. Okay, now let me go back. Displacement of land surfaces. Let's go back to that picture that I really liked from last time. I think I already passed it. Yeah. Okay. I think we're coming up on it fairly soon here. Here it is. So what was your displacement here? I mean, you can't tell for sure, but I would say 4 to 6 inches, just looking at that. Here comes somebody trying to get in. Here's Asher coming in. So let me mark Asher here. Okay. All right. We should have, let's see how many people we got now. Should be 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually, somebody must have left. I can't tell for sure who it is. That was probably some of those dings or pop-ups that we were getting earlier. Okay. And for those who just got here, Asher and Labrina, maybe some of the others that came a little later, where we are now in Chapter 19, Building Earth's Surface, we're now on page 491, Measuring the Earthquake Strength. I went back to show you this picture here. This displacement looks like to me, I'm just guessing 4 to 6 inches. That's pretty significant in my mind. Okay. This was just an illustration here, and this makes no sense at all. A road is what? 25 feet wide? You don't have that kind of displacement, but they were just giving you an illustration. Okay, I can't get it to advance back to where we were. Here we go. Okay, so early on, that's what we did. They measured effects and said, what was the strength of the earthquake? Well, using that approach, they had what they called the Mercalli scale. Now, I don't know for sure who in the world Mercalli was. He sounds like he may have been Italian. I don't know that for a fact, but I'm guessing maybe. They do have a lot of earthquakes in Italy, so that wouldn't be surprising. Think if you've ever traveled to Rome, you'll know a lot of the damage that was done to, say, the Colosseum and other things like this often was done by earthquakes. So they do have a lot. We have friends that live in Italy, and there's always shifting going on. You also look in Italy how many volcanoes they have. Mount Vesuvius, Mount Etna, I think, is in Italy. So yeah, there's lots of activity going there. So not surprising if he was Italian that that's where it came from. Mercalli scale. Now, its relative intensity compared to others. So a number 1 on the Mercalli scale is basically one you don't even feel. Okay, you know it happened, but you don't feel it. Up to 12, which is total destruction with visible ground waves. You actually see the ground moving out like that. Ugh, that would be awful. Total destruction. That's the Mercalli scale. Again, based on what we see. Structural damage to buildings, fires lit, landslides that happen, displacement of land surfaces, tsunamis created in the water, and how big and how strong they were. Okay, that's the Mercalli scale. Measuring the effects is not the best way to measure earthquakes. Okay. Now here is a blurb. Now I don't think it shows up again. I believe that's a later one that we see something like this, and it has the real small type, and then later it'll show better type. And this just popped up again. I don't know if someone's coming in, going out, or what. Let me see. Nope, don't have anyone waiting. Okay. So, these are the earthquake safety rules from the National Oceanic and Atmospheric Administration, often called NOAA. N-O-A-A, NOAA. Okay. So if you ever hear on the news, and NOAA says this, and NOAA says that, that's not a person. That's this organization, National Oceanic and Atmospheric Administration. They're the ones that study this kind of stuff, including the weather and other things like that. If you're there during the shaking, this first one's sort of hard to do. Don't panic, okay? But frankly, if you're there during the shaking, the worst of it's already over with by the time you have time to react. So there's no reason to panic. If you're okay, the odds are you're going to stay okay, especially if you follow the rest of these. So there's no reason to panic. that doesn't mean your adrenaline doesn't start pumping and you get pretty excited about it. Now, it says if you're indoors, stay there. In other words, by the time the first big quake happens, if nothing's falling on you, you're probably in a pretty safe place. Okay? But not a bad idea to get under a table or some other type. Oh, somebody must have just left because we had a total of 12 before, and now we're down to 11. So hopefully these folks will be coming back because we do have a lab today. But get as much protection as you can. If you have one of those safe rooms that would work in tornadoes, the odds are they work pretty well for earthquakes as well. Okay? They actually say under a doorway is not bad because generally the lintel, the part that goes over the top of the door, is reinforced big time. So that's usually stronger than your walls are. So that's actually not a bad place to be. Now, they say stay away from glass. So I'm sitting right in front of windows here. If there was an earthquake going to happen, I'm going to move interior. Okay, I'll probably also go downstairs. I'll probably also have to go downstairs because our dog would be coming upstairs. Otherwise, she is a scaredy cat. Okay, dog. Okay. Now they say don't use matches, candles, or any open flame. If you've got something going like a fire in the fireplace, put it out. Because a lot of times, and if you'll notice here, it says fires. Why would earthquakes cause fires? Well, mostly this. If you have natural gas lines, and just about every city does, then when you have an earthquake, some of those gas lines could rupture and break. And if you happen to say, oh, the lights went out, where's my matches? You turn them on and then kaboom. You've just lit your whole house on fire, including you. So candles, matches, any other open flames, or if you already have a fire going like in a fireplace, put it out because you don't want that natural gas. If something does leak, you don't want it getting near the flame. Okay? Now, that's if you're inside. If you're outside, move away from buildings. Don't go running into a building. You don't know if that building will suffer damage or not. So stay outside. Stay away from buildings. Stay away from power lines. They could come tumbling down on you. And frankly, I don't know if you know this or not, the power lines are not generally insulated on the outside, and therefore they can shock you dead. Okay, if they fall on you and you're grounded, you're going to be part of the circuit then. You don't want to be there. Stay in the open. Don't run through or near buildings. Okay, not a good idea. Because quite often after an earthquake, there are what they call aftershocks, and if something was damaged or loosened in the building, and then you have an aftershock, here it could come tumbling down. Okay. Now, if you're in a moving car, good idea to bring it to a stop as quickly as you can, safely as you can, but stay in it generally. Because the car then acts as the springs, the tires, and everything else act as if, they can soften the blow to you. They can mitigate the shaking. Okay, so stay in it. The car springs will absorb some of the shaking and will offer you some protection. Now, they didn't mention this here, but I'll go on to say it. Remember that earthquake I told you about along the San Andreas Fault that happened in Los Angeles? It was within just a few months of the one that hit San Francisco during the World Series. That one, a whole lot of highway overpasses collapsed. So therefore, if you're in a car, don't say, oh, here's a nice shaded, protected area, let's go there. Don't go there. Stay out in the open. Sort of the same thing you see here. Stay in the open. So move your car to somewhere in the open. Probably not near big trees, not near big buildings. Get it somewhere out in the open, certainly not under an overpass, and stay there and stay in your car. Okay. Now, after the shaking has happened, and usually it doesn't go on that long, check but do not turn on utilities. Okay. If you can in any way find out if everything's okay, do so, but don't turn them on. If you smell gas, open your windows, shut off the main valve if you know where that is, leave that building, because anything could create a spark, and then it could go. Report the leak to the utility, but don't re-enter the building until it's been checked out by your professionals. If water mains are damaged and you have leakage, shut off the main valve if you know where that is, and if electrical wiring is showing, in other words, you've had enough shaking, you see wire poking out of the wall, then close the switch at the main beater box. You don't want anything arcing and sparking if there could be gas leak as well. Now, if you have power, and most of the time you're not, if you have an earthquake anywhere close by, more than likely you're going to lose power. Just like they're saying, when is it supposed to happen? The hurricane rains and winds going to show up here. Is that sometime in the today or tomorrow, isn't it? Has anyone heard? Okay, y'all must not be listening. My wife was talking about it earlier, but not today, so I don't know what's going on now. But it says, if possible, if you can, turn on the radio or TV for emergency bulletins. But the odds are, if you've had a major earthquake, power's going to go out. Now, if you have radios, and some of the weather radios are this way, they will run on batteries for a while, or actually, I think my wife got some that you can crank and run for 10-15 minutes per crank, after you crank it up real good, so you can find out real short reports, if you need that. Stay off the telephone except to report emergencies like gas leaks and things like that. The telephone lines, the whole infrastructure system is going to be stretched to the max. So stay off the phone except to report emergencies. Hang on, you can find out later, because you can't do anything about it then if everyone's okay. Stay out of severely damaged buildings that could collapse in the aftershocks. That's where they're coming into play. Do not go sightseeing. You'll only hamper the efforts of emergency personnel and report crews. Now, unfortunately, do y'all remember back in, 2011, when we had the major tornadoes that came through the area? It looks like somebody else left the class. If you remember that, some people went out. Oh, I heard the Pleasant Grove got hit. I heard this and that. And they went out to see. Well, guess what? All they're doing is clogging the highway. You're not going to be able to see, because they probably got everything blocked off, or there was so much damage you can't get through anyway. And what you're going to do is get in the way of, say, the ambulances, the fire trucks, or even the cleanup crews. They can't get through to start doing their job. Okay, so don't go sightseeing. Same thing's true with tornado type things. Don't go sightseeing. You'll see plenty of it when the power comes on. They'll show it over and over and over on the news, so you'll get to see it. Okay, so that was sort of stuck in here in the middle of everything else. I think it does show up somewhere in the book. Yeah, top of page 492. Okay. Now, let's get back to measuring earthquake strength. And it won't advance until I click on the slide. Okay. Now, nowadays we use something else, not the Mercalli scale. We use the Richter scale. Okay. Before we get to that, though, on page 491, there is a myths, mistakes, and misunderstandings. this author loves these. Do earthquakes swallow people? I know in the movies that's what it looked like. The earth opens up and people and cars and everything else fall down in the big crack. No, it doesn't happen that way. That is complete fiction, not even science fiction. That's just fiction. Okay, so let's move on from there. So now on page 492 is where we're talking about the Richter scale. Now here's another name. Now I know his first name. His name was Charles Richter. Based in California, I believe, perhaps a professor at Caltech, I believe he probably was, California, where we have lots of earthquakes. He came up with a scale that's not based on effects, it's based on how much the earth really moves. Not on how many buildings fell down or how many gas leaks you had or how many fires. Those are all vary place to place. Okay? His was based on the actual swings in the seismograph recordings. So he was probably instrumental in getting these seismographs all over the world so that they could measure them. Now, on this Richter scale is what we call a logarithmic scale. Now, I don't know if y'all are familiar with logarithms, but here's an example. Think of the number 10. Then think of the number 100. Well, 100 is 10 times as great as 10, right? On a log scale, 10 would be represented by the number 1, 100 would be represented by the number 2. So it would look like it would be just twice as much. That's what a log scale does. It takes huge events and brings them down to something that's more manageable. So, if you see something reported as a 5.6 on the Richter scale, and you see another event, 6.6 on the Richter scale, that's not just 1 point more. The damage, the energy, those kind of things will be 10 times what the lower would be. That's what logarithms do for you. So on this scale, a 3 is not felt. On the Mercalli scale, a 1 was not felt. On the Richter scale, a 3 is not felt. You can measure 1, 2, and 3. You're never even going to feel them. You'll just measure them. Anything beyond 3, you start feeling. Okay? So that's how you sort of make a connection. On the Richter scale, the 9 is the largest measured so far. And that's been measured a few times. The main one I can recall reading about is a major earthquake that happened in southern part of Alaska, whose tsunami made its way all the way to Hawaii and did damage there. I mean, that was a very powerful earthquake. So 9 is the largest measured so far. That doesn't mean we can't have larger, but that's the largest measured so far. Now, here is basically what we know about the Richter scale. The 0 to 2, now 0 means you don't measure anything. 1 to, anything between 0 and 2, that's the smallest you can detect with the seismograph. 2 to 3, you can detect it, measure it, but you usually can't feel it. Okay? 3 to 4, you feel it as a very gentle shaking, no major damage done, just a gentle shaking. And remember I told you about the sign, the wall art that fell off of our wall when we were out of town. When we came in, we found it on the floor. Well, what's going on here? They said, oh, that's probably from the earthquake. It did just enough shaking to knock the thing off the wall, but no major damage. No cracks in the wall, no foundation things, nothing. It just shook a little bit. Now, that same earthquake up in D.C., which was much closer to the epicenter, which was somewhere in Virginia, in Washington, D.C., the Washington Monument was damaged enough. So that would have been a Up there, that would have been probably something beyond maybe a 4 to 5 local damage. Okay, down in Georgia, 3 to 4 by the time it got there, a very small. Okay, 4 to 5 minor damage with local, minor earthquake with local damage. 5 to 6 moderate earthquake with structural damage, not just little cracks and things, but actually foundations move. 6 to 7 very strong earthquakes with destruction. 7 to 8 major earthquakes with extensive damage and destruction. 8 to 9 a huge earthquake, basically total destruction, and that probably corresponded sort of with the 12 on the Mercalli scale. Okay, now this is all based though with how much movement those seismographs measure. Okay, the amount of movement, not the amount of damage. Now, I think I may have already given you this example before, but I can't remember. I've taught this class so many times I can't remember who I gave it to. Excuse me just a second. My throat is getting so dry. I've been talking all day long. Okay. It was near Christmas. I'm guessing about a decade ago. Some of you may remember it. The island nation of Haiti was the epicenter for a pretty significant earthquake. Okay? And unfortunately, right in their capital city, the densest populated part, that's where the epicenter was. I mean, boy, was Haiti ever shaken, literally, in every way possible. Buildings fell down, roads, power, everything was interrupted. It was awful. Now, a few months later, there was another earthquake, and they said that had nothing to do with that one. This one was in Chile. That's the country on the very border of the Pacific Ocean on the western coast of South America. And of course, that's where you have subduction of the Nazca plate underneath the continental, South American plate, and there was a major earthquake there. Now, it did damage. It damaged buildings, it damaged probably power, damaged all sorts of things, but because Chile was right on the place where earthquakes usually happen, the Chilean government had put strict building codes and other things into effect, and therefore the damage that you would have measured on the Mercalli scale was probably minimal. Okay, because that's the effects, the structural damage to building and stuff. They had great building codes there, so you would have rated that a smaller earthquake than the one that hit Haiti. Another thing is probably the epicenter of that one was probably not in a high population density area, so the major shaking, oh, here comes Jackson again. He's been here and now is coming back. Let me make sure I do have him marked here. Yes, I do. Okay. So, on the Mercalli scale, they would have rated Haiti stronger than Chile, the one in Chile. But in reality, the actual movement of the earth, Chile was probably close to 10 times the strength of the one in Haiti. Probably almost a full point on their Richter scale, which would have been 10 times the intensity. So that's why Richter scale, and I won't advance until I click on the screen. Okay, so that's what we have on the Richter scale. So even though there was way more damage in Haiti, the main reason for the damage, buildings were made just out of concrete blocks, not even reinforced steel. And so when something shook, they just fell apart on people. I mean, it was devastating there, but mostly because they didn't have strong building codes. Frankly, they didn't have much history of earthquakes, so they didn't think they had to have strong building codes. But just like the one in Virginia, who can account for that? Or the one in Missouri, who can account for that? Wasn't near a major earthquake area, but still it happened. Okay. Oh, here it is. This is the one. I thought it wasn't on the slide. This was the very thing we saw in that fine print. Here it is in much bigger print. Earthquake safety. Same things we read before. I won't read those again. But here you can see it a lot more easily. Okay. Can't think of anything here that they didn't say before. Now we move into 19.4, the last section in the chapter, I'm pretty sure. And I am going to say this. On your page 493 in your book, before you get the origin of mountains, they talk about tsunamis. What tsunami is, and they mentioned them briefly before, let me go back and see, is when they're talking about the Mercalli scale, the tsunamis are tidal waves that come out of that. Okay? Back when the slides were done, the tsunamis were mentioned in chapter 24, Earth's Waters. They weren't brought up in great detail here in chapter 19. When they did one of the editions of the books that's happened since then, they moved tsunamis to this chapter, not to chapter 19, took them out of 19. So, 24. So in a few weeks, not many weeks, we'll be doing 24. That's where we'll see the slide on tsunami. But please read it here because it is very significant here as well. And let me mention a couple of tsunami type events. There was, I'm guessing 5 to 6 years ago, it may have been longer, a fairly major earthquake happened off the coast of Indonesia. Now that's in what they call the Ring of Fire, the Pacific Rim, and that's where you had probably oceanic plate subduction. So, and it's also very close to the plate boundaries between the Indo-Australian plate and the Asian plate. Lots of things going on there. They have a pretty strict they're used to them. I mean, it's a place that these things happen, but it's hard to get used to them because there's some things you just can't do with it. Pretty major earthquake happened just off the coast of Indonesia, shook Indonesia pretty badly, and I think Thailand and many other countries real close. But the tsunami, the tidal wave, made its way all the way across the Indian Ocean and hit the east coast of India. And we have friends who were from what we used to call Madras, it's now called Chennai, in Tamil Nadu state in southeastern India. And Madras is pretty close to being a port city. It sits inland a little bit, I think, up a river channel or something like that. But that tsunami hit, and it was in the warm time of year. People were out on the beach, and the tsunami hit, and there was very little warning. A lot of people did get drowned. And we had our friends had family members they didn't hear from in several days, but they ultimately, as far as I know, heard from everybody. I don't think any one of their relatives or friends were ones that were affected by the tsunami. Okay. The second one of those, and this happened more recently, there was a major earthquake. Again, the Pacific Rim of Fire, they call it, Ring of Fire, Pacific Rim countries. Japan. Japan is one of those island countries that has been formed by repeated volcanic activity where the oceanic plate, the Pacific plate, subducts under the Eurasian plate and causes all sorts of havoc there. And they had along that fault line that occurs there, I don't know what kind of fault that is, transfer I guess they call them transfer fault or a converging fault, whichever it is, or boundary region there, it's major. Well, Japan, because they have absolutely no coal, very little fuel, I mean, no oil reserves, nothing else, they had to buy all their own energy. So when nuclear power became a big thing and a pretty safe thing and a fairly green thing, they dedicated a lot of funds and effort into building nuclear power plants. Now, nuclear power plants have to have water sources to cool the reactors and things. So they're usually built near rivers or the ocean. Well, this one plant, Fukushima, was built near the ocean, unfortunately right on top of the fault line. Okay, not a smart thing to do, but the fault lines basically define that edge of the island. So where else are you going to build them? You had to be near water. Well, they did, and when they had a major earthquake there, the tsunami that came, it didn't well, it didn't do as much moving away from the island as it moved to the island. And basically that tsunami swamped, totally swamped, my understanding anyway, the nuclear power plant. I mean, it was that major. Well, when it did that, all the power went off, okay, because they were the generating source of power. They lost it, okay, and when that went off, there were no ways to sound alarms and things like this, that the reactors were now in danger because there was no cooling going on. It was an awful, awful mess, and they had what could have been probably the worst nuclear disaster that the planet has ever had. Fortunately, they have built enough safety features into their plant construction and design that everything worked out much better. They did have some damage, but we're not nearly as bad as somewhere like Chernobyl. Chernobyl, that overwhelmed everything they had. This overwhelmed what they had, but they had so much redundancy in place, it was somewhat contained. Now, I don't know if that's somebody coming or going. Let me see. It looks like we still got the same number. Okay. Now, so just wanted to mention those two tsunamis that have occurred, or three tsunamis that have occurred relatively recently, not super recently, but one of them, the one in Alaska, that was way before my time. Okay. So now we're in 1904 on page 493, the origin of mountains. Now, what is a mountain? A mountain is an elevated part of the Earth's crust that rises abruptly above the surrounding surface. Okay? It can be caused by one of three ways. They mention two right here. Created by folding of the Earth's surface, that could form a mountain. Faulting of the crust, that could form a mountain. Or, and they mention that below, volcanic activity, which could also cause. Now, this is Sancho. Allison has not been in yet today, so let me mark Sancho here. All right, we're getting up to being a fairly good crowd, but we've been losing people too. We're only missing Avius, Brianna, Deja, James, and and Drew, I think. But we're probably missing some others now that have come and gone. Hopefully people will be back. So we're just beginning on page, we're in chapter 19, Building Earth's Surface, 19.4, Origin of Mountains. We're just starting that on page 493 if you got the big book, or 1913 if you got the smallest book. And we're looking at mountains, three basic origins: folded mountains, faulted mountains, or volcanic activity. Okay? Now, all of those are happen basically because of plate tectonics. Plate tectonics is responsible for a whole lot of this stuff. Okay, it won't advance until I click on the slide. Now, let's look at faulted and faulted mountains. Top of page 493, right-hand column. A real neat picture here. I don't remember if that's shown on the slide set. If it's not, I'll show it to you. We have some domed mountains. Okay, begin as a big, broad, arching fold called an anticline, arching anticline. Okay, folded mountain mostly happen somewhere really deep. Folds happen where the rock is pretty hot and it bends but doesn't break. That's a folded mountain. The overlying sedimentary rocks weather away, leaving more resistant granite peaks. That's mostly what you see in the Appalachians. Not, maybe you shouldn't say mostly. You see a lot of it in the Appalachians. And that's what the next picture is going to show. But this shows the dome happening. Okay, it's rising up there. The surface, now they don't mention this here, we're going to talk about it in the next chapter. Because it's getting stretched like this, it tends to crack and be fragile. And then where that happens, rain and wind come in and wash or blow it away. And you're left with then the underlying areas, which could be resistant granite peaks. It could be limestone. It could be other things like this, but they're mentioning mostly granite. Okay? Once erosion has occurred. Because the sedimentary rock that were put down in layers, it tends to weather pretty easily. We'll talk about that more in the next chapter. Okay. Now, before we move to the faulted mountains, here's that picture I was referring to. This is an aerial view of the Appalachians. And part of this is the Great Smoky Mountains, the Blue Ridge Mountains. They're shown here. Most of these, a large number of these, are folded mountains. Probably folded many. In fact, the Appalachians are one of the oldest mountain ranges on the planet. Okay, most of the other major ones we know, the Rockies, the Sierra Nevadas, the Andes, the Alps, the Pyrenees. I mean, all those came along much later, but these were mostly folded mountains. Some faults in them, I'm sure. I don't know that any of them are volcanic. So that's the Appalachians. But over the years, they've worn down. They used to be some of the biggest on the planet. Now they're pretty small, pretty minor. The other newer ones are much bigger. Goodness, I need something to drink. Okay. Now the fault block mountains, that's where faults have occurred, where thrust faults or normal faults, some sort of faults, they rise sharply along a steeply inclined fault plane. Okay? Just as you would expect. Now weathering does erode the sharp edges, but most of these fault block mountains, especially if they're fairly recent, they're very jagged looking. Whereas the Appalachians, if you go to them, they're very rounded because they've weathered. They were folded to begin with, many of them, and they've undergone a lot of weathering. They're actually getting shorter all the time, the fault block mountains. If the pressures are still there, they are probably rising all the time. Okay. This looks like that same picture we had of the graben and the horse. Don't sweat that. That's not really all that important. But whereas the faults occurred and they were pretty sharp and jagged at one time, over time the weathering wears this down, wears that down, and when it wears this down, it fills in the lower lying areas like here and here and here and here, while this is being worn down here and here and here. So you get a little more rounded peaks, a bit shorter peaks, and especially they appear shorter because the residue from them has then added to the valleys, so the difference between the valleys and the mountains are greater or less. They were greater back here, less here, because not only have sediments built up in the valleys, the peaks have worn down, the sharp edges especially. Okay, so that shows basically if the faulting is still happening, they can be pretty jagged. Okay. Here are the Tetons. Now, we've been to the Tetons a few times. Magnificent mountains. Very, very angular. Those are definitely fault block mountains. No folding there. Very jagged fault block mountains. Okay? And they just rise. This is, by the way, my guess is what they call Jackson Hole, Wyoming. If you've ever heard of that, a lot of movie stars and people like that have places out there. It is a pretty flat area with these mountains just rising up amazing. So that description they had here of mountains in general, mountains, elevated part of the Earth's crust rising abruptly above the surrounding surface. Jackson Hole, very flat. There goes the Tetons, just abruptly going up into the air. And that's exactly what you see. Whoops. Oh, in that picture I showed. Okay. So now we move to volcanic mountains. A volcano is a hill, doesn't have to be a mountain, or a mountain formed by the extrusions of lava or rock fragments from the magma below. Okay, underneath the surface is molten material. That's what we call magma. Underneath the surface is molten material, magma. Now, when a volcano erupts, sure, magma comes from below. As soon as it reaches the surface, it's then called lava. Okay, the lava comes up, but that's not all that comes up. When that volcano blows, sometimes it's been capped, sometimes a really thick cap, for hundreds or maybe even thousands of years. When that finally blows, wow, rock fragments are moved up. And so you have all sorts of things. It's not just molten lava. You also have rock fragments. And that could also come from the magma below. It could be bringing up rock fragments that it's brought up on the way up. Now they mention here the structure, the vent, the crater, and the lava flow. But they never illustrate them. In fact, I can't even remember if the book does any more than just name them just like that. Okay? So I'll try to give my best rendition of this. I can pick out two of these. Right here, there's the crater. That's obviously the crater, that part in the middle. The lava flows, you can see those. Those are running downhill like this, okay? That's the lava flow. Now, the vent, what in the world do we mean by the vent? Now, to me, that would be the little areas that come out. Now, I can't tell if this is just cloud hanging over the mountain or if cloud coming out of the mountains. That's what I am estimating would be the vent. Okay, where if there is a source of steam or something like that, that could be a vent. At one time, probably the crater was a very small vent, but after several explosions, it's blown up. Now, I'm pretty sure this is Mount St. Helens. Now, I don't know if you Were any of you alive back in 1980? Probably not many. That would have made you 40 years old. A few of you may be 40. I doubt it. I don't get to see you, so I don't know. Here's Christian. He had to get out and come back in. I'm pretty sure I've already got him here today. I do. Okay. Now, Mount St. Helens, the same picture pretty much that they have in the book. Okay. Figure 1920. But this was the top of Mount St. Helens several years after the 1980 explosive eruption. Okay. And the author obviously took that picture from a plane or somewhere up there. Oh, here's Drew. Drew's here today. Okay, good deal. He was one of the ones I was saying we didn't have. So now we have Drew here. So now today, we may be missing some more by now, but who hasn't been here? James is not here. Deja's not here. Brianna and Avius not here. Those are the only ones that have been here that are not here now. Hopefully we'll still get them in.
Afternoon, Mr. Charles.
How you doing?
I'm all right.
Good.
How about you?
I'm doing pretty well, thanks. This is Drew?
Yes, sir.
Okay, good deal. I just can't see who was lit up, but it sounded like your voice. We're talking about volcanic mountains. We're on page 494, 495, chapter 19, building their surface, and certainly mountains are part of building their surface. We're just talking about these and about the eruption of Mount St. Helens. It had been an extinct volcano. They thought it was inactive volcano, all these names, and in 1980 it became active again. Now, unfortunately, in 1980 I was 29 years old. Okay, so I remember Mount St. Helens. I don't remember where I was when it happened, but I could figure that out. But anyway, it blew. And this is several years later. You can see the lava flows went down here. Nothing has grown back. It was probably pretty lush and green beforehand. It's still nothing grown back. Okay, it takes a long time for that to form soil again. It looks like maybe a lava flow went all the way down there. I can't say that for sure, but it looks like it could have. But it looks like pretty major lava flows. But not only lava, there were probably chunks of rock that came up with that too. Now, we talk about volcanic mountains and you think that the lava flow builds the mountains up. And most of the time it does. Mount St. Helens actually made the mountain shorter, because when it took the top off of the mountain to make this new crater, they lost height. It went tumbling down the hillside here, okay, and then got probably covered up with lava flow. But it actually wound up shorter than it was before because it literally blew its top. Okay, so anyway, now I have to click the slide before it'll advance. Okay. What are the various types of volcanoes? Three major ones. The first of these is called the shield volcano. It's constructive of solidified lava flows. Very little rock fragment. Could have some, most of it's lava flow. Most of the time, because this was a liquid and there was no major explosion that made it happen, it's a broad, gently sloping cones, if you even see the cone. Here's going to be an example of one right there. I can't remember if this is Haleakala or this is Mauna Loa. Okay, one of the many volcanoes in Hawaii, because Hawaii is a volcanic island chain, and this is Mauna Loa. And I think I've mentioned to you before, I don't know if people in the Navy had a weird sense of humor, but they named ammunition ships after volcanoes. And I was on the USS Kilauea, which was a fine ammunition ship, but it was named after the most active volcano on the planet. Okay, Mount Kilauea in Hawaii. Mauna Loa was also fairly active, but you see there's no obvious activity going on now. Here's an old crater, there's a smaller crater, there's a crater. This looks like that could have been a crater. But what happened, the lava just sort of oozes up and runs down the slope. making this broad, gentle sloping cone. Not much of a cone at all, but somewhat of a cone. Then you have what they call the cinder cone volcano. This is constructed mostly of rock fragments. There probably is some lava in it, but mostly of rock fragments. These are steeper than these shield volcanoes, but tend to be smaller. So they're fairly small in size. We don't have a picture there. There are some in the book. Let me get the one in the book and show you. Here is a cinder cone volcano. I don't remember what name that was. That's the Sunset Crater, a cinder cone volcano near Flagstaff, Arizona. And as you see, it's not all that big. Very pretty, very symmetric pretty much. It looks like there has to be lava involved with that, but it's mostly rock fragment. Okay? Generally doesn't get that tall. Okay? Steeper, but smaller than shield volcanoes. And then you have your composites. And the composites are these things like you see here. Okay. Now, let's go back to Mauna Loa. Oh, there they showed that. Okay. This is basically what's happening. You just have repeated lava coming up, spreading out, so you have broad mounds. They're more like hills than they are mountains, okay? Now, I'm guessing this is what they call a vent. That would probably be at the crater. This would just be a vent. It may form a little crater. This may be a vent. They don't ever describe this, but it's just slowly oozing out and spreading, making the shield volcano. Okay, here is the composite volcano. It has alternating layers of cinders, like your cinder cone volcano, but then also ash and lava flow with volcanic mud. Now, they don't really describe what volcanic mud is, but my guess is it's sort of the powdery soil-like material that maybe was on the mountain has been picked up by the lava and carried along. It's not lava, it's not cinders, but it's sort of just like water carrying away your topsoil and making mud. Okay. Now here again, they show this thing but don't identify. There obviously is your crater. Here obviously are your lava flows, but it can also be ash deposits, older lava flows here. They still don't show what they mean by vent. The only thing I can figure, these are the things that come out to the side here. Those would be the vent. That looks like maybe an old vent right there. Maybe one over here. Okay, and maybe the crater itself was or is a vent. They just don't say. Here is one of the magnificent mountains in California called Mount Shasta. Our sister ship in the Navy was Shasta, an extinct volcano. We were a very active volcano. That was I don't know if someone just came out. Let me see. Nope, don't have anyone waiting. These things pop up and I can't tell if anything's behind it or not. This to me looks like that's an old crater there. Well, obviously that doesn't look like a crater there, so this must have been a place where Shasta blew its top and actually lost ground rather than getting taller. But look at these lava flows. You can almost see where this was molten rock and now hardened to be these lava flows here. A little bit less so down here. Maybe some of this is what they call the ash and volcanic mud here. This could have been some volcanic mud too. They don't really describe it too well. Very, very tall mountain in Northern California. Beautiful mountain, Mount Shasta. Near Seattle, you have Mount Rainier, another gorgeous mountain, an extinct volcano. At least they're hoping it stays extinct, okay? That would really wipe out some pretty major area there. Think of Boeing and Microsoft and just all the areas, things that are out there in the Seattle area. So those are your composite volcanoes, the big, beautiful, very steep, very tall mountains. Okay. Again, it won't advance until I click on the slide. All right. Now let's look at other features. Not all magma makes its way to the surface. A lot of it tries to, but not all of it makes its way to the surface. It doesn't all become lava. It doesn't all explode. It makes its way up, but at some point either slows down, cools off, hardens, and forms other features. Most of the magma remains underground. Okay, I don't know what the noise is there. Let's see if anyone else is coming in. Nope, don't see anybody. Okay, most of the magma remains underground. It cools and solidifies to form intrusive igneous rock. Igneous because it was molten, intrusive because it cools inside the earth. So that means it cooled fairly slowly, making large crystal sizes, and some of the structures that come out of that would be, one of these would be a batholith. Remember, lith means rocks or stones or things like that. Batho, I don't know what it means, probably something about being interior, underneath. This is large amount of crystallized magma, large content. Let's show the illustration here. If I can get the illustration to come up. There it is. This would be your batholith. Now, it never made it to the surface. The surface eroded away, and now it's on the surface. But it didn't make its way to the surface by itself. It was just magma that forced its way up, but didn't quite make its way to the surface. These layers here, the sedimentary rock, at one time continued on over this, covering the batholith, but now they've eroded away, leaving you the batholith exposed. That's a batholith. Large amounts of crystallized magma. See how big that was? Okay. A stock is a smaller protrusion from a batholith. Okay? So the batholith is a big protrusion. The stock is a smaller. Batholith intrusions can cause hogbacks. Okay, what names these are. The hogbacks are where you see, originally the sedimentary rock was here, settled out over time, over much time, but the magma forced its way up and folded the sedimentary rock upward here. So now the layers of the sedimentary rock that were the edges of different kinds of rock, uneven here because they're different types of rock, they form what's called the hogback. That's what remains that didn't erode away of the sedimentary rock. All that was sedimentary rock across the top that the batholith forced upward, bending, probably cracking, and then it eroded away, leaving the hogback here and the batholith here. The stock may at some point make its way to the surface. This shows it hasn't quite made it there yet. Now, smaller than stocks, you have the dikes. The dikes are the vertical or near vertical protrusions, usually smaller than the stocks. These might actually make their way to the surface at some point. Okay? And this would be a dike that made its way to the surface. It's just a ridge here. Sedimentary rock on this side, sedimentary rock on this side, but right in the middle, igneous rock. So you know something strange has happened there. Okay? The sills. Sills are where the magma is coming up through the dike, but then finds a weakness between layers and starts a horizontal layer. Those are your sills. The verticals are your dike. The horizontal are your sills. Now, if you were drilling here, you drill through sedimentary rock, and then all of a sudden, whoa, what did we hit here? Hard igneous rock, dark, iron-rich igneous rock. What is it doing there? And then in no time, you're through it. That's a sill, very thin layer. Okay. And then the last of these is the laccoliths. Okay. It started out as a dike, making its way up, but then forced, sort of like the batholith did here, but in a smaller scale, because the batholith was big all the way down. Stocks were big down here. This was a very small dike coming up, but then it found a weakness, folded up that layer of the sedimentary rock. Some of it probably eroded away. This over here looks like that's a litholyph, that some of the sedimentary rock is remaining on top, but you form these sort of conical shaped things. Sometimes you get erosion, and this would form some of those arching folds that we were talking about earlier, created by the laccoliths. Okay, they didn't quite make their way to the surface, just like the batholith didn't, but they were from a very small source, whereas the batholith was from a very big source. Okay, those are some of the other features you will find in certain areas of the country. Okay, not so much around here. Okay, but these were layers of sedimentary rock that have been interrupted, messed with by the magma intrusions, and these were all different types of magma intrusions. All right, what's our overall picture here? Okay, trying to find where we are here. This is on page 499. Okay, and we'll go back and look at a couple of other things in a minute. Well, actually, let's do it now because I'm liable to forget. So let's go back and look at this. This is a really interesting article here. Volcanoes change the world, and they literally have and will and continue to. As someone mentioned in my Sunday school class Sunday, Mount Vesuvius really changed Pompeii's world. In fact, it wiped it completely out. Okay, that has happened, but not just local like that. These change big time. They mention several here, and I'll mention a few of them. I'll just read through it quickly. Volcanic eruption certainly changes the local landscape. That much is obvious. Mount St. Helens wiped out things in the local landscape. We heard about it, but it really didn't make much difference to us. But there was a volcanic eruption back in 1815 to 1816. The volcano was Tamburo in Indonesia, the Ring of Fire we talked about earlier. The Tamburo eruption was massive, blasting huge amounts of volcanic dust, ash, and gas high into the atmosphere, such that, and by the way, some of the stuff that comes out is sulfur dioxide, which basically forms sulfuric acid. So it can cause lots and lots of issues. Okay, but much of the ash went up into the upper part of the atmosphere and changed things for years. Not just in Indonesia, half a world away. Okay, they mentioned here it snowed in New England of June of 1816 after Tamburo erupted in 1815. Why? There was so much ash in the atmosphere, not enough sunlight came through, and when it didn't come through, the land was cooler, and it actually snowed in June. It was known as the crops failed. 1816 became known as the year without summer. Okay, that was a long time ago. In 1982, now I was around then, I don't remember much about it, Mount El Cajon or something like that in Mexico created enough haze in the stratosphere to reflect 5% of the solar radiation away from the Earth, and researchers also estimated the El Cajon eruption cooled the temperature a few tenths of a degree for about 2 or 3 years. But then it came back. I mean, these are compared to global warming, which is a long scale thing. These are only 2, 3 years, 5 years, something like that, but usually things come back to what they were before. There was one more in June 1991. The Filipino volcano Mount Pinatubo erupted, blasting twice as much gas and dust into the atmosphere as El Cajon had about a decade earlier, and it remained in the Earth's atmosphere for a decade, the next 10 years. The haze from such an eruption has potential to cool the climate. So there is global warming, but there are other things that cool it. The other things so far have been sort of temporary. Doesn't look like global warming is going to be that temporary. Okay, so that is a fantastic blurb. When we went over that in class, it was probably more than a decade ago. A student was in my class at the time from the Philippines, and she said yes, she remembered that because her family, somebody lived fairly close to Mount Pinatubo. She did her research paper on that one. It was a pretty good paper, especially since she was involved locally with it. Here's the person behind the science. His name was James Hutton, and this is 26 to 97, so he only lived about 70 some years, which is probably pretty old for that day and age. He was Scottish, I'm pretty sure. Yeah, Scottish natural philosopher. Well worth a read. Several other names are mentioned here, may lead you to paper topics. This cannot be your source. It can be your source of ideas for the paper, but not a source for your paper itself. Okay. Now, the last, let's see if this is on the slide set. Yes, it is. So I won't show that last one. So here we are at the overall picture. Mountain ranges are composites of many different processes. Now we're talking about the whole range of mountains. Let's say the Rocky Mountains or the Appalachian Mountains. Okay. Many different processes, each uniquely structured. You can have folded mountains right next to faulted mountains. Okay. And you can have volcanic activity in between. Now the Appalachians, again, probably no, if any, volcanic activity at all involved with them. If it was so long ago, I'm not sure you can recognize it. However, the Rockies have quite a bit of volcanic. The Sierra Nevadas, I think, do too. And certainly what we're going to look at next, they do as well. And I'll pull that away. Especially apparent along converging plate boundaries, where one plate is subducting under another plate. Okay, and here is such an example. That little bitty Juan de Fuca plate, probably one of the smallest plates around, is subducting under the North American plate here. Down here you have transform boundary. This is a converging boundary. Okay, where it's subducting under, notice as soon as you start hitting this, you get these mountains being formed. Many of these are volcanic. There's Mount Shasta. I don't know if Lassen Peak is or not. Crater Lake in Oregon is, from what I understand, a beautiful, beautiful lake. My nephew, when he was on his way to catch his ship in, I think he went all the way to Hawaii to get it, but he drove across the U.S., probably left out of somewhere near Seattle or somewhere near San Francisco. I don't remember which, but he took a tour. It took long enough to do it, so he went by Crater Lake and said it was absolutely gorgeous. But notice here, where this has been subducted, you get these mountain ranges because it subducts way underneath, and then the mountain ranges form. Many of these are volcanic. Some of them may be folded or faulted mountains. What's the surprising thing is you get these. Notice they call it, this is North American plate, but these are plateau basalts. Where did we read about basalts? Basalts were the oceanic crust. That was a basalt. Was there at one time or another? Was this part of the ocean? And this plate activity happened so much that this was originally a oceanic plate, and it's subducted here. Here's Kundra coming back in. I'm pretty sure we got her earlier. Yep, there she is. Okay. We don't know. It's interesting, but my wife and I drove through some of these basalts. She had meetings in Salt Lake City down here. And by the way, Salt Lake, why is there a Salt Lake right in the middle of the continent here? Could it have one time been part of the Pacific Ocean? Possibly. It's what's left over. Who knows? Here's basalts nearby, plateau basalts, meaning they're fairly flat. They've just been uplifted as plate tectonics has been happening over millennia. Okay, long periods of time. And where these break up, then you have the volcanic mountains here. Okay. I bet you this is part of a fault line right here that separates Vancouver Island from the rest of British Columbia. Who knows? This is Vancouver, is a great city here. So you see this kind of stuff happening, and there are the mountains to prove this is going. And this is why it's called the Ring of Fire. Where is Mount St. Helens? There it is right there. The most recent to have blown. Most of these others we say are extinct. Give them time, they may come back. Now the very interesting thing, and you don't quite see it here, what does anyone know what's right in here? Somebody I think in the class mentioned it earlier. Yellowstone National Park, the first, the biggest, well, maybe not biggest, but most impressive geological feature I've ever can imagine seeing. Okay, and it sits as a huge crater of a volcano, and this is right at the Continental Divide. So there has been some major stuff going on here centuries ago. If that ever blew again, Katie bar the door. Okay, that could cause some really major damage in many ways. Lots of this area could be really shaken up. Salt Lake City, the biggest population center around there, but lots of things could be messed up. Okay, that's the overall picture, and I think if I can get my slide to advance, that's the last one. So that does finish chapter 19. And like I say, every chapter, nothing replaces reading the chapter. So if you haven't read it already, please read it again. Please read it before the end. Now at the end of every chapter you have a summary, and this has to be one of the shortest summaries I can remember seeing. There it is. Just right there is the summary. Now it's followed by key terms, and this is not a very long list of key terms. I go to the top of the next column here. So it is a fair number, but still not that many. I think that's one of the smallest group. But then the next group, applying the concepts, and this one has 50, which is probably a little above average of applying the concepts. Multiple choice questions, excellent thing to study for your test for chapter 19. Now remember, chapter 19 test is probably going to have the fewest number of multiple choice questions that you've had. It's mostly fill in the blank. I've tried to hit all the high points that I could think of, but also stuff is hit. But still, these are still great questions to study. Then questions for thought, there's 17, maybe a little bit below normal. For further analysis, 4 below or right at normal. And then there's an invitation to inquiry about earthquake patterns. So they give a website or so if you want to go there, there's a few questions they ask. And then the parallel exercises, again, I found those less instructive than they were in the first part of the book, where you really have those kind of exercises to worry with. All right, any questions on chapter 19? Again, after lab today, I will put the test out there, and believe it, don't be surprised, it's a one-page test. That's all there is, folks. comes out being a total of about 17, 18, 19, something like that, blanks to fill in or things to do. So it's about a normal number of possible answers, but they're all condensed on one page. And that's why I made it before a take-home so people could use a book to do it. And you can do that always. Any questions on 19? All right. So I'm going to discard my annotations and we'll move on to chapter 20. Hang tight. Here. Okay, I know 20 was up here. I bet you it's behind here, so let me click OK here. No, I don't see it there either. This just hacks me off why things that was there has now disappeared. Let's see if I can get to it this way. Well, no, better this way. There it is. Okay. Now we'll do, there it is, chapter 20. All right. Now, whereas chapter 19 was building the Earth's surface, chapter 20 is shaping the Earth's surface, which also means wearing it down. Okay? Anytime you shape something, you tend to wear it down. Okay? So let's get the slideshow set up for the current slide. And here we go. Shaping the Earth's surface, chapter 20. All right. Core concept here. And by the way, this picture is slightly different from the one in the book. The one in the book is colored. You can still see they're similar type things. This obviously was sedimentary rock. You can see it's in layers, layer upon layer upon layer upon layer. Now this may be part of the Grand Canyon, I don't know, or some of the other canyons out west. It's definitely a western type deal. There has been a lot of shaping going on here. These layers down here are the very oldest, newer. As you go up, what has worn this down? Mostly water flow. Has eaten through layer upon layer upon layer. Okay? And you're left with this. I'm guessing it's the Colorado River, especially if it's Grand Canyon. That would be what it is. It may be one of the other great rivers out west. Okay. Core concept here on your page 505 or 20-1. The surface of the Earth, we're talking crust type surface, is involved in an ongoing process of destruction and tearing down of higher elevation and building up the lower elevations. Okay? Now let me get this out of the way. Again, you can't see it, but I can, and it's smack in my way. So let me move it over here out of the way. This, I've been here. Not right there, but really close to here. This is in Yellowstone. This is the Yellowstone River coming through here. This is, I think, the upper Yellowstone Falls. Okay, now if you had seen this a little bit broader shot here, you would see that the stone, the rock on this side, is mostly a very ochre type color, yellowish color. That's where the park got its name, Yellowstone National Park. The rock is sort of a yellowish kind of tint on this side of the Yellowstone River there. Now, this river has been eating through that rock for millennia. Running down, running down, running down. Lower down here is a second, the lower Yellowstone Falls. Another beautiful waterfall. And I've seen that one as well. We've been up here on the edge of this one. I mean, that water is moving. This is highly resistant rock, like granite here. This was probably a lot of sandstone in here that got eaten away really badly. This is still being eaten away. At one time, this is where the water went. Other time, this is where the water went. One time, the water was at the surface up here, but it's eaten away, eaten away. The surface of the Earth is involved in an ongoing process of destruction and tearing down at the higher elevations and moving things to a lower elevation. That's that's the core concept of this chapter. Okay? Can't advance until now, in your text, you see sedimentary rock too, but these have a lot more erosion going on around them. It's a very pretty shot, but it doesn't say where it is, I don't think. No, it doesn't give where that one is. But that rock has been sculpted out by either rain or wind. This was obviously by water. Okay, so what are the processes that do this? Okay, now actually 20.1 they don't even have on the slide. Usually they do a little bit of overview, which is on page 506, and you see a beautiful, beautiful arch there. And usually when you see that, that could have been water at some time, but a lot of that is being sculpted by wind erosion, because you just don't see that much water there anymore. But it may have been started by water, but then ultimately also done by wind. So 20.1 was one paragraph long. It said weathering, erosion, and transportation. Okay? And we'll talk about each of those terms separately. This is 20.2. On the first page, already 2 sections in, weathering. Now, what do we mean by weathering? Weather has something to do with it, certainly. But what we mean when we're saying weather is changes, slow changes generally, resulting in the breakup, the crumbling, and otherwise destruction of solid rock. Now, if you recall back when we did chapter 17, we were talking about rocks and minerals, how you build rocks, okay? Pressure, the compaction, the lithification processes, those kind of things. Here we're doing the reverse. We're slowly breaking up, crumbling, and otherwise destroying solid rock. But remember, this was part of the rock cycle. Weathering was mentioned on there. Remember that illustration you had. What was igneous rock is broken up by weathering and becomes sediments that then become sedimentary rock, and then maybe becomes metamorphic rock, and maybe goes back to being igneous rock. That was the rock cycle. Okay, this is the process of tearing down, destroying. Now, 3 types of weathering. They're going to focus on 2 of them, but there are 3 types. Physical weathering, and on the next slide they're going to call it mechanical weathering. Physical, mechanical, almost synonymous, meaning the same thing. Chemical weathering, we'll talk about that to some detail. And then finally you have biological processes as well. They don't do quite as much about it, or when they do, they sort of talk around it. I'll try to bring a few more of those out in the open. Okay. Now, all of these contribute to the rock cycle, what I was just talking about before. Okay. But they also contribute to the formation of soils. Thank you very much. This is my specialty. This is what I did my graduate work on. Formation of soils, studying soils. I was a soil physicist. Okay. So this, I love it. And it has 1 slide, just a couple paragraphs is all they give to it. But without soils, we don't live. Because we wouldn't have food sources. The animals we eat wouldn't have food sources. Nothing would do. Without soils, we can't. So that's a positive thing of the breakup of rock, is you form soils. But the negative side is you lose soil. Okay. The same processes that break up the rock also make you erode the soils, which you're going to get to in a minute. The weathering also contributes to movement of rock materials over the Earth's surface. And we'll talk about how some of those have been really major in the formation of our country, in fact. And then finally, erosion. Erosion is usually a negative thing. Formation of soil is a positive thing, in my mind anyway. A rock may not think so, but I would think so. But erosion is a process of physically removing weathered materials, which would include soils or other materials, and you're taking out of the picture, therefore losing it. Well, temporarily anyway. Ultimately, it's going to build up layers again and maybe form sedimentary rock again, and slowly through the rock cycle come back into play. That takes an awful long time. It doesn't take much time for, in some circumstances, for you to lose a lot. That's erosion. Okay, so let's look at the three types of weathering. The first of these, like I said before, on the last slide they call it physical weathering. Here they call it mechanical weathering. Same thing. The physical breakup of rocks without any chemical change. Okay? Now, here are just a few examples of that, and we've already sort of hit on some of them before. The first of these is the disintegration processes, and the first one's called wedging. Now, that's not just something you did to your younger brother. No, we won't get into that. But wedging can be caused by something as simple as frost. Now, that certainly would not be a big feature here in the southeast. We just don't get that cold. But it does happen in some areas and can happen big time. And here's what happens. For some reason, this rock got a microscopic crack in it. Okay, maybe the crystal structures were a little weaker there. There was something that dissolved away there. It got a hairline crack in it. Well, guess what? Rainfall came, filled the crack with water. Okay, later it turned very cold. The water froze. Now, water is just about the only substance on the planet that when it cools, and water does do what it's supposed to. Generally, water, when it cools, it shrinks. Like everything else, it shrinks. But then at some point, 4 degrees Celsius, that would be about maybe about 40 degrees Fahrenheit. At that temperature, when water is getting ready to become its crystal structure of ice, because in the crystal structure of ice, the molecules actually move further apart to get in their crystal structure. So when it does that, it expands. And between 4 degrees Celsius and 0 degrees Celsius, water expands big time, really big time. And you know this. I don't know if any of you were around, I'm sure you were, but whether you remember the Arctic vortex that came through probably 5 or 6 years ago. It was just really, really cold, just incredibly cold Arctic blast that came down in the middle of winter. And I mean, we got down into the single digits. When that happened, we actually had pipes to burst. And there, in the coldest time of the year, we had water running down under our house, pipes burst. We had to call people we knew. He called a plumber he knew. And ultimately, they had to come out in some really miserable weather, tear up the floor in our utility room, do all sorts of things. But we had a really good construction guy. He got everything put back into place. But boy, it was major. Well, if water can break steel pipes, it can certainly break a rock. So what happens, that water gets into that microscopic crack, it freezes, it expands, it makes the crack bigger. Then more water the next year gets into that crack. Oh, here comes James. Good deal. Okay. I was wondering where he was today. Okay, because I don't think he had missed a day yet. And I thought, why is he doing not here today? So now we're only missing Deja, Brianna, and Avius. So maybe some of them will got. Now maybe we're missing others that have left, but glad you're here. James, we finished chapter 19 and we're starting chapter 20 right now. We're talking about mechanical weathering, which is also called physical weathering. This is on, I haven't turned the page here, page 508 or so. Okay. No problem.
My internet's been out.
Oh, okay. I'm sorry. I've had that happen to me too. So mechanical weathering, physical breakup without chemical change, just the breaking apart. Okay? And water can cause that, especially when it freezes, it expands and breaks rock up. Okay? Uh, it does that year after year, making the crack bigger and bigger. At some point, that piece of rock becomes two pieces of rock, two smaller pieces of rock, and in the process, some of that could have been broken down more. So that's one, wedging. Now, tree roots will be doing the same thing. My wife's family has a place up, or had a place up on Smith Lake. Now it belongs to us because they wanted to, her parents wanted to sell it, keep it in the family. We didn't have children. You buy it, so we bought it. Um, but up there, you can see places where tree roots literally look like they're hanging onto rock. And here's how it happened. They found those microscopic cracks. And the little root hairs, which is where all the activity of the root happens, they go down into it. Now, this would be part of sort of mechanical weathering, but this would be more the one I said they left off. If I could get it to go back, I have to click on the slide to make it go back again. Biological weathering, biological processes. They mention them here by trees, which is definitely biological, but they mention it under mechanical weathering. But you see, biological weathering could involve other things as well, because those tiny little root hairs, they are finer than, I don't have much, but I have some hairs here. They're even smaller than a human hair. They get their way into that little crack. And what they do, they're searching for that water that's down there. They're also searching for nutrients, because quite often the rock has in it pretty good nutrients, but it's fixed in the rock. So what those sneaky little root hairs do, they secrete an acid. And that acid eats away a little bit of the rock and dissolves it, and then the root hairs suck up the mineral they were looking for. Clever little boogers they are. Okay? And over time, they make the go down deeper into the rock, and meanwhile they grow into bigger roots, and that wedges the rock apart. So not just water freezing to ice, but also roots growing down here, growing into bigger roots and pushing the rock apart. And you can go up to Smith Lake sometime, and you can see some of that happening. It looks like trees are just growing into the rock. They did it really, really slowly. The other form of mechanical weathering is called exfoliation. And we've actually talked about this before without using that term. Now again, the term folia, right, you see in the middle, same root as what you have in foliage, the leaves on a tree, or a portfolio, that would be a collection of documents you had, leaves as in paper. That's what folia are, layers. And this is talking predominantly about sedimentary rock that you've had that pressure from underneath, like a batholith or a laccolith or something pushing it up, and when it does push it up, it spreads it further apart. That's exfoliating the layers, breaking those layers apart. You have reduced pressure on the top side, increased pressure on the bottom side, pushing upward and exfoliating. Now, you ladies may have exfoliated your skin. What are you doing then? You're taking off that outer layer of older sort of chipping skin that was there and getting down to the fresh new skin, right? Same type process, you're losing the outer layers. Okay, the fractures are caused by expansion of underlying rock, increased pressure on the underneath side, spreading apart the surface on the other side, on the upper side, and that spreads it and ultimately causes erosion. If you've ever been to Stone Mountain, not one of my favorite places to go, but if you've ever been, you'll see lots and lots of gravel around the base of the mountain, mostly because it's exfoliated as that rock came up out of the ground, however that happened. Okay. Here are the tree roots. Now this is not rock. This is a sidewalk, but that's almost like rock, okay? And tree roots just push it right on out of there, okay? These are the tree roots that originally weren't, they're just little bitty root hairs that went down into crevices of rock and slowly over time ate their way in, forcing the rocks to break apart, secreting that little bit of acid, breaking it further. So that's a combination of mechanical weathering, physical weathering, a little bit of chemical weathering by secreting the acid, and certainly done biologically too. So that's the trees doing the wedging. Okay. Any questions on that? Okay. I don't know what was there, but there's nothing there now. Let's move to chemical weathering. Okay. Now that's along about page 509. Okay. Now chemical weathering is decomposition of minerals. You're actually decomposing them. You're breaking them apart by chemical reactions. Physical reactions are just breaking bonds, but it's still the same mineral you had there before. Chemical reactions are the chemicals come down here and actually eat away, dissolve, break up, not just, excuse me, I've got hiccups, physically breaking the things, but basically dissolving the bonds. Okay. Now they mentioned 3 different chemical reactions here. This first one actually should be in a pair. Anytime you have oxidation, you also have reduction. And sometimes you'll see this referred to as redox, Re from the reduction part, OX from the oxidation part. Anytime you have oxidation, you have reduction. So both of these contribute, but we're most familiar with the oxidation. These are reactions with oxygen. And if you remember back when we started about the solid earth materials, we said things like the vast majority of the Earth's crust is made up of oxygen. Okay, it's the #1, wasn't an element in the Earth's crust because it's just all over the place. Well, this is actually reactions with gaseous oxygen, like we usually think of oxygen, but this forms those oxides and silicates and other cates and ites and things like this that form. These are the reactions with oxygen. Now, some that we're familiar with, when iron gets exposed to oxygen, especially if there's a little bit of moisture present, it rusts. It produces red iron oxides. The red iron oxides are never as strong as the original iron minerals were, so that will help break these apart. And a lot of your red soils you see, especially over in Georgia, but also here in Alabama or anywhere in the southeast, the redness you see is from those red iron oxides. Very, very tiny little particles of iron oxide coating the surfaces of clays. Okay, that's what forms our red clays. Little bit of iron oxide just on the surface of those clay particles. So that's oxygen. Oxygen reacts with just about everything. Okay, and usually when it does, it's in the process of breaking down chemical bonds. #2 is carbonation. Now, I really don't like this term as well. I didn't like oxidation if you don't include reduction, but carbonation, really, the better term here would be acidification, making an acid. Okay, because what do they say? It's reactions with carbonic acid. Well, carbonic acid is just one of many acids that you have present in nature. This is carbon dioxide combined with water forms carbonic acid. Sulfur dioxide combined with water forms sulfuric acid, a way stronger acid than carbonic acid. Nitrogen oxides combined with water form nitric acid, a way stronger acid than carbonic acid. I already mentioned sulfur. There's just lots of things that combine with water to form mild or weak acids. Carbonic is just one of them. That's carbon dioxide combining with uh, with water. In fact, I bet you some of you, in fact, I may have in your presence drunk some. This is a Coke. Now, it may have, if I can read the label here, no, it has phosphoric acid. I thought it did. But if you've drunk a Mountain Dew or a Sprite or 7 Up or something like that, the odds are, or my wife loves these sparkling waters. That's carbon dioxide dissolved in water. What she's drinking is carbonic acid, not particularly great for the teeth, not particularly great for some other things, but it's usually pretty weak. But that's all it takes. That weak acid will dissolve limestone. Remember limestone? A chemical uh, chemical sedimentary rock. Okay, you have clastic sedimentary rocks, which are your particulates, and chemical sedimentary rocks, and this breaks down that chemical sedimentary rock of limestone. Carbonic acid will do that, and that's why you have a lot of the limestone caves. I've never been up to is it the Soda Springs up in northern Alabama? Really pretty park up there that's made up of limestone caves. The DeSoto Caverns, that's it. Okay. Really, you've been there, I take it, right?
Yes, sir.
Isn't it amazing?
Giant maze.
Oh, yeah. That's limestone that has been eaten away by small amounts of carbonic acid that's dissolved in the water, eating away that limestone over time. Amazing. That's a form of chemical weathering because you're actually breaking down the chemical structure of those um, of the minerals. Okay, whereas physical weathering is actually breaking the chemical bonds but not destroying the actual mineral. This is destroying the mineral. The third one of these is hydration, reactions with water. Believe it or not, water is one of the most active chemicals we have. So this could be called, and that's why it's called chemical weathering. Okay, water is a great dissolver. It dissolves stuff, includes dissolving in water, combining with water. Water will dissolve lots and lots and lots of things. That process is called hydration. Extra water added, breaking down chemically the minerals that you originally had. Carbonation, guess what? Acids dissolved in water. So water's there too. What did I say about the iron oxides? Water acts as a catalyst. It's not actually part of the reaction, but it sponsors the reaction. And why that came up, I don't know. Okay. So those are examples of chemical weathering. Here, and this picture is also in your book. It's not entirely clear, but you see these are sedimentary rock here, probably limestone rock. That's sort of how they form. And where water has gone in, it's where the weaker limestone was formed, water has dissolved it away, making these caves. You can see where some of them are. The caves that were done, water dissolving away the chalks rather than the hard limestone. Here the water has cut the channels through here. This one time was rock here. Water has dissolved it away, eaten it away, especially the weaker rock, leaving the harder rock here. Up here it ate away this side but left this one. So water has been involved in every bit of that chemical weathering. Okay. Unfortunately, I think it's time. Yeah, we have passed time. We're going to start next time with soils, the most important part of the chapter, don't you think? Okay. That's because I was a soil scientist. Okay. So let me put the marker here. We got through 20.2. We will go through 20.5. So we got a little more than half the chapter left, approximately. I think we can finish that in the first 2.5 hours next time, and probably have our lab for chapter 20 next time as well. We'll see. I think we probably will make that. Sometime coming up, we're probably going to have another super long day that we don't have time to get the lab done, but we'll see. We're moving along, folks. We're in chapter 20 now. We only have 23 and 24 to go. Well, no, yeah, after this, but we've still got 20 to do. But we're in week 5. We've got week 6. Yeah. So we're moving at a pretty good pace. We may sort of slow it down a little bit, especially when we have these labs. They'll slow us down a bit. So, any questions? 19 or 20? All right. What I'm going to do now, do y'all need to take a little break? This is a good natural breaking point. I don't know, you see, have to sit here the entire time. Y'all, I'm sure, get to get up and move around. I can't tell what you're doing. I really don't care what you're doing. I'd rather you be paying attention, but I know you can't always be here for the whole time. Do you need to take a break now, or do you want to just keep on trucking? It's up to you. I just did a dumb thing there. I took out the slide before I closed the slide set. I mean, took out my DVD before I did. Let me go back and close this slide. Okay. Okay, I think I got both of those closed now. So now I can take out. Let me make sure. I know screen sharing stopped. Give me a break. Okay, let's see what we got here. Close that out. Okay. All right, I think I can remove the disk now. There we go. This computer, for some reason, takes a long time to respond. It's a fairly new computer, so I don't know why it does, but it does. Okay, so I never did hear an answer. Do you want to take a quick break or not? Anybody? Huh? What you say? Yes, sir. Okay. So I'm going to pause the recording. Be sure to tell me to turn the recording back on. I turned it on this time, but I'm going to pause it. It was all spam. And then I also thought, well, looks like it could start getting some rain soon, so I wanted to check and make sure no packages. My wife's been doing so much buying by mail, so we don't have to go out and get exposed. So I wanted to check and make sure nothing had been delivered. The mail had come, so I got that while I was out too. And the dog was wanting a little attention, but I didn't give her much. So anyway, it just took longer to get all that done. So I apologize for that. Now, any questions before we get started on the lab today? Let me just see if I have it open already on the share screen. Yes, there it is, Blackboard. So I'm going to open Blackboard. Well, I've got to sign into Blackboard. Okay, such an awkward way to sign in. I guess y'all have to do this too. You can't hit return, you have to do something else. Now the reason I'm going to Blackboard, not to get in Math 237, that's where I was last time. Oh shucks, that's not the one I wanted. Let's go to courses. Okay, I need to go near the bottom to find this course. Okay, we're getting close. There we are. That's us. Physical science. Okay. Now, there was our Zoom announcement. I guess all of you got because you're here. And I'm going to move this thing. You can't see it, but I can. But people who might be watching the video, that will be in their way as well as my way. So let's move that out of the way. And let's go down to weekly activities. Okay, now I'm going to have to move Angelita. She's in the way here. Okay, no, y'all can't see this. I couldn't get to this here. Click on this down arrow here, and let's go down to week 5. That's where we are. 5 out of 8, folks. We're over halfway through with this course. There's week 5. And instructional materials, lesson plans, PowerPoint, handout, blah, blah, blah. That's where we go. Oh, yeah, no. Yeah, I started the recorder. I couldn't remember if I had or not. I'm paranoid about that. Here are the labs. Lab 6. Here's the PDF. This is the one that came out of the book. Now you notice it has an icon, but it doesn't underline, so you have to go to the 3 dots, click on that, and it says download original file. So I will do it that way because it's easier. I could do it another way. Yeah, I'll show you how to do it this way. So here's the original file. There it's opening. Wait till it opens. Now it's open or downloaded. So you click on it again, it opens. And it's sideways. And if I remember correctly, you say right key, and then rotate clockwise. There it is. Latitude and longitude. Okay. Well worth a read here. Okay. This is going back to things we did before because, you know, building our surfaces, we can't really create volcanoes. We can't, do things. So let's go back to this. What we're going to talk about are the parallels. Those are the circles that, if we had a globe here, the circles that get smaller toward the top and smaller toward the bottom, biggest at the equator, they're all parallel to each other. They're called parallels. They are what you use to measure latitude. Okay? How far up, north or south of the equator you are. Now, the ones that roll from the pole to all the way to one pole to the next pole, all around the earth, that way, those north to south, those are your meridians. We talked about our local meridian that goes due north to due south through where we are. That's a meridian. Every one of those is a meridian line. The one at Greenwich Observatory, it's a naval observatory in London or near London, England. It's not in London, but a little to the east of it. It's called the prime meridian, and you measure longitude along your meridian lines. Now the longitude goes from 0 at the prime meridian all the way halfway around the globe to 180 east or 180 west. Whereas the parallels go from the equator 90 north or 90 south. So different numbers there, and there's a reason for that. Okay? Now, we're not going to mess around with soft clay, the materials, or these procedures. Basically what you do is read this. I see some things that you'll need to read right here, how they talk about you break the degrees into minutes and minutes into seconds. That's going to be things you need to know. But we are going to deal with the concepts that are here. So let's look at the concepts. All right, let's imagine that we did have a globe, okay, made out of soft clay. And you cut it horizontally halfway and vertically halfway. And then you took a protractor, remember what those were, set it on here, and the degrees north of this equator, you're right on the equator here, that's where you cut it across that way. And you read from a few degrees, 15 degrees, 20 degrees, 30 degrees, 60 degrees, 80 degrees, 90 degrees. 0 to 90 is your northern range of your latitude, 0 to 90 north. Going south, you go 0 to 90 south to get to the South Pole. Okay? So you put protractor there, and you would read how far north or south you are from the equator. Okay? Now, if you place the protractor on the flat part down here, okay, the horizontal part, Oh, here it is on the vertical part. And you see what you read is 20 degrees north, 40 degrees north, 60 degrees north, 70 degrees, 80 degrees, 90 degrees north. That would be right at the North Pole. Flip it over and do the same for the South Pole. 20 degrees south, 40 south, 60 south, 80 south, 90 south. Then at the South Pole, you'd be at 90 south. Exactly. That would be corresponding to your latitude lines. The latitude at any point would be how many degrees you are north or south of the equator. Okay? Now, placing on the flat part here, that same protractor, this is the prime meridian here. Place it right there and measure how many degrees this would be east of the prime meridian. You'd be going through Africa down here, Asia up here, Europe up here, moving into Asia, more of Africa, then the Indian Ocean here, and more of Asia here, until you got around to the Pacific Ocean at 180 degrees. So you go 0 to 180 degrees east, or if you did it on the other side, crossing the Atlantic from prime meridian, cross the Atlantic, get into the U.S., and we would be right over here about 89 or 90 degrees west. 80 some degrees, 86 maybe, somewhere over there. That's where we live. Okay? Keep on going around to California till you get back into the Pacific, and then somewhere in the Pacific there's your international date line, back there at 100 degrees west or 180 degrees east. 180 west, 180 east. That's what you measure your longitude by. So, the first 5 points, the first 5 values on your test are right down here. What information does latitude of a location tell you? Now, I've just said it sort of quickly. Go back and read the first part of the lab. You'll find the answer to that. Then what information does the longitude of a location tell you? Go back to the first part. That part I sort of went through pretty quickly. You'll find the answer to those two. Now, third part, we get down to practical stuff. According to a map or a globe, and if we were in class, I would have these atlases out there for you. The Alabama Atlas, the U.S. Atlas, all these atlases out here. What is the approximate latitude and longitude of the place where you live? Now, if you can get your hands on an atlas, you can look it up there and find out what your latitude and longitude is. If not, you can find it somewhere on the internet. Y'all are used to doing this. I'm not as used to it, but I can probably even find it, okay? Find latitude and longitude where you live. If you're in a certain community, say Inslee or Fairfield or Birmingham, or I don't know if they'd have anything like Southside Birmingham. That's where I live, Forest Park, or Irondale or McCalla or whatever. Wherever you live, see if you can find it either on a map, on a globe, or on the internet somewhere, and record here your latitude and your longitude. Now, when you give your latitude and longitude, remember, latitude is a number between 0 and 90 degrees, and you live in the northern hemisphere, so you better have north on this one, okay? So you have to give, yes?
Are these the questions we're answering for the lab? Like, is this the actual lab?
This is the lab. These are the first 5 points of your lab right here. That's what I'm going over now. Okay, you'll need to go back and read that first part to answer these two, and then you'll need to go either on the internet or get a map, atlas, or something like that, and find where you live and write your approximate latitude and longitude where you live. If you remember from the earlier labs, the first or second lab, no, second or third lab, I guess it was, when we did do that, I gave it from Bessemer because I had that one memorized, okay, what the latitude was. Anyone remember that one? You can go back and check your labs and you'll find out. I think it was the second lab, around about the 4th or 5th page in the lab. What is the latitude where you're living now? It's going to be in the 30s north, okay, around 33 something another north. So give as much detail as you can. We never mention longitude, but I'll just tell you, it'll be in the 80s west. So if you don't get something like that, have it make sense. Now, if you do go to some sites on the internet or something, they may give it differently. They may give pluses if you're north of the equator, negatives if you're south of the equator. So if you run into a place like this, convert that to be, if it's a plus latitude, make that north. If it's a negative latitude, make that south. Same thing with longitude. Sometimes they'll give the pluses to the east, the minuses to the west. We're in the west, so that may be, if you find that you're at a minus 89, you can write that as 89 or whatever the number, probably not 89, but 89 degrees, so many minutes, so many seconds west. We're in the western hemisphere, so we're west longitude. We're in the northern hemisphere, so we're in the north latitude. Okay, does that make sense? Okay, those are your first three questions. All right, let's move to the fourth question. And that's the one I just pointed out to you. Explain how minutes and seconds are used to identify a location more precisely. That was near the bottom of one of those pages in that printout. So go back and get that. Now, this fifth question, you may have to wait till the end of the lab to answer it. Was the purpose of this lab accomplished? Okay? And unfortunately, that's all they wrote here. There's this invitation to inquiry. It really doesn't tell you much. Okay? There's a little bit there, but it's not much. And we did most of that in earlier labs. So that's where we go to. I got to move y'all out of the way again, I think, because I want to go to here. Well, where is it? There we go. This was the lab there. I'm going to the document here. Okay, that was the first part of lab 6. Only 5 points worth there, 5 questions. Answer those. Mostly from the reading. You'll get one from there, from the internet or a map or something. Here's the second part. This is the Word file, the doc file. Okay, I'm going to click on that. Oh, wait, you can't click on it. You have to go to the 3 dots here. Click on that. It says download original file. Click on that. It starts downloading here. And now it's finished downloading, so I can click on that. And basically what we're going to do here is continue what you were doing with question 3 before, which is the latitude and longitude where you live. And here's where we pick up. So you notice it starts with question 6. Pick any city in Alabama not in Jefferson County. Now, if you live in a city not in Jefferson, oh, wait, here's Kenda back in. Okay, she's out of the, oh, wait, I don't have my sharing, sorry. Go back and share this. Okay, sorry, I forgot I wasn't sharing. Okay, pick up in number 6. You'll need to find a source on the internet or an atlas, that would do just as well, where you can find latitudes and longitudes of any city in the world. So start off with any city in Alabama. Now, if some of you don't live in Jefferson County, Alabama, I think most of you probably do, but if you don't, then pick a city not in the county where you live. Okay, if you've already done in question 3, now is McCalla in Jefferson County or is that in Tuscaloosa County? Anybody? I don't know. I think it's still in Jefferson, but I don't know for sure. Does anyone know? Anyway, if you live somewhere not, so say you're in Vance. Vance I know is over in Tuscaloosa County, or at least I think it is. So if you live in Vance and you already did Vance, then pick something not in Tuscaloosa County to do the second one. So pick a city in Alabama, write down the city here, and then give the latitude and longitude for that city. Again, you'll need numbers here, and I'll tell you it's going to be something around in the 30s, I'm guessing, here. And then you'll have minutes and seconds here. Longitude's going to be around the 80s or so. Oh, and this will say north because anything in the northern hemisphere is north. Longitude will be something in probably in the 80s or so here, and that will be west because we're west of the prime meridian. Okay, so remember your latitude and longitude always has numbers and a letter. Latitudes have north or south, longitudes have east or west. E or W, latitudes have N or S. So then, after you picked any city in Alabama not in your home county, then pick any city in the U.S. not in Alabama. Write down the name of the city, any city you want, and then find its latitude, its longitude. Now in the U.S., those are all going to be N's for north. Now here you could have a great bigger, you could have 30s, you could have 40s, you know. If you're up in Alaska somewhere, you could be 50s, 60s, or 70s, I don't know. If you're down in Hawaii, that would be probably in the 20s, okay, the latitude. But they'll all be north. Longitudes are all going to be west, I can tell you that. They could be from 80 somethings, maybe upper 70s, maybe over to 90s, maybe even 100s and some. Those would be your longitudes. You'll probably have minutes and seconds with it. Okay. Pick any city in Canada. Record its latitude and longitude. So write down the city here. The latitude, I guarantee you, is going to be in north. So be sure you have your N there. And it'll be about the same range of latitudes that U.S. I'm sorry. These will be probably in the 40s, 50s, 60s or so. Longitudes will be about the same range as anything in the U.S. Okay. Pick any city in South America. Now some of these may be north, but most of them will be in the south. They'll all be in the west, I guarantee you, for longitude. But pick the city, write down the city, give me its latitude and longitude. Then go over to Europe. Okay, my phone's ringing again. I don't know what the deal is today. It's just ringing off the hook. But I'm not going to mess with it. Pick any city in Europe. Write down the city here, and you probably need to give the country too. Anything outside of Canada, like South America, give the city and country. In Europe, city and country. Latitude, in Europe, all going to be north, I guarantee, but these latitudes will be anywhere probably from the, again, 30s up to the 60s or so. Longitudes, a few of these will be on the west, most of these will be in the east, okay? Just depends on which city you get. They will be pretty low numbers because they're fairly close to London, England. But you could get as high as maybe 40 or 50 degrees west. No, east. Pick any two different cities in different countries. Pick any two cities in different countries in Africa and record their latitude and longitude, okay? So again, you put the city down and the country. City, comma, country. City, comma, country. Make sure these are different countries. They'll certainly be different cities. And then latitude and longitude. A lot of these latitudes may be south because a lot of Africa is south of the equator. Some of it is north of the equator. For instance, Cairo, Egypt would be north. You know, several would be north, but many of them would be south. Longitude, most of these are going to be east. Maybe a few would be west. Most of them will be east. But they will, I don't know, be fairly low numbers to probably in the 50s or 60s or so. Then go to Asia. Pick any two different cities in different countries in Asia. And that would be city, comma, country. Be sure you put the country down for anything outside of Canada and the U.S. and pick city, comma, country. The latitudes here are mostly Asia, all going to be in the northern latitudes. The longitudes are mostly going to be in the eastern longitudes. Could be a few in the west, but I doubt it. Eastern longitude. And then pick one city in Australia, put its name. You might even put its the state or province it's in. It's not necessary. Pick a city in Australia and then put its latitude. I guarantee you its latitude is going to be south. All of Australia is in the southern latitude, the longitude, I guarantee all of it is going to be in the east as well, because nothing is past that. Okay, so what does that give you? That gives you 26, no, I'm sorry, from 6 to 13. So that's 2, 4, 6, 8, 10, 12, 14, 16. I got to move y'all again. Kendra, you're in the way again. Okay, let's do it again. 2, 4, 6, 8, 10, 12, 14. And as I go on up, 16, 18, 20, 20 plus the 5 we had, 25. There's your 25 points right there. That's your lab. Okay. And just like we've done on some of the other labs, I can stay online with you as long as you want me online, and I'll answer questions, let you know whether what you're doing is right or not, or I think it's all pretty self-explanatory. Does anyone need me to stay on for questions? I'll be willing to stay. Any questions whatsoever? Any of you? Now, something I just want to point it out to you. I can't do it with Diana in the way here, so I'm going to have to move you again. Notice here, if you're trying to type on this, you have to enable editing before you can type on that. So if you are using your phone as the internet or something, however you're doing this, remember you do have to enable editing before you can do that. There, I just did. I didn't mean to, but I did. Whoa! What happened there? Screen sharing stop. I didn't mean for it to. So let me go back to that. Okay. Now I got to move this out of the way. You can't see it, but people watching from home on YouTube videos will. Okay. Any questions? Okay, Diana, your light's on. Did you have a question? Anybody have a question? Okay. Do you want me to stay online in case you do have questions? I'm here till, well, I'm here all night. I mean, I live here, but I'll stay on as long as you need me to. But if you don't need me to be here, I'll be glad to get off and start trying to print out labs and other things you've turned in already. So let me know what you'd like to do. I do notice people are checking out themselves, so I understand that. You don't need this open to do your lab. What is lab number 7? Oh yeah, no, that's for the next chapter. We aren't there yet. Yeah, lab 6 is for chapter 19. We just finished chapter 19. We started on 20. We're not going to get to that lab until we finish chapter 20. Yeah, good question. Okay, gotcha.
Hey, Mr. Fowler.
Yes.
Is it okay if we put the first 5 questions on the bottom of this document right here?
Absolutely. Just make sure that, okay, a few things to make sure. Make sure you put your name somewhere on everything you send me, okay, please. Okay, most of the time if it's not there, I'll catch it, but sometimes if I'm printing thing after thing after thing, then I get back and start grading, I say, whose is this? Okay, and I've already deleted, or they're all mixed up and I can't tell who came from where. Okay, so please put your name. But other than that, yeah, you can put anywhere you want to. Let's just see. I'm going to have to move. Matthew, you're in the way again. Okay, so you can't see that, but, well, where is my, there it is. Okay. I'm near the top now. You can write some things across the top if you have room there. Okay, and like you said, you could put things at the bottom if you have some room there. Yeah, you have a little bit of room there. So yeah, you can put those first 5 questions on this piece of paper if you want to. That would be perfectly fine. Or you can just take out those, 2 pages? I think everything was on 2 pages there, and just send me those 2. Or just type them in on a piece of paper. That would be fine too. And send it with this one. Yes, just get me the data. Show me the data. That's what I want. Did that answer your question?
Yes.
Good. Any others? Great questions, by the way. Keep asking. Okay, do you want me to stay on with you? I'll be glad to do so if you have more questions. Or you can contact me any way you can contact me. I've got a little bit of stuff to do in Blackboard to shut things down. I've got things to do on YouTube video to shut it down. So I'll be here right at the computer. We're down to 8 people now, so we're losing them, dropping them off here. Any questions? Do you want to stay on or not?
I think it's a good you leave.
Okay. So first I'll do is stop the sharing. I'm sick and tired of sharing with you now. So I'm just kidding. So I'm going to stop sharing. And unless there's some final questions, I'm going to end the meeting. But don't end your work. Keep going. Any questions? Now, if anyone comes in later, we've still got an hour plus, hour and 15 minutes or a little more than that even. If they come in now, we're through. So sorry about that. If anyone gets in touch with me, tell them that the recording will be out there on YouTube probably by the end of the evening. This is a long class. It's been going almost 3 hours, so it's going to take a while for this to load onto Blackboard, and then onto YouTube, and then I've got to move it to the playlist. But it'll be there sometime this evening, hopefully. Okay? Yes. Okay. Okay. All right. Let me show you again. All right. I think it was this one here. Okay. This is in Physical Science. Can you see that? Physical Science 111. This is in Blackboard under Instructional Materials, Lessons, PowerPoint, Videos, Handouts, and so forth. Starts with the PowerPoints here. We're probably not going to do all these this week, but I just put them out there in case we need it. Has all this other information here. Here are the 2 pieces of the lab. The PDF, that was the one from the lab manual that talked about latitude and longitude, showed the illustrations, and had the first 5 questions right there. Then the one we were just looking at, that was from the doc file, the Word file, and that showed from question 6 to 13, but those had multiple pieces to them. Okay, so that's where you get those labs. Don't worry about... Yes, it's in week 5. I'm sorry, I didn't say that. Week 5. Okay, got it? Okay. I'm sorry, I should have said that. Week 5. Yeah. Okay. Any other questions? Great questions, by the way. I'm glad y'all are asking now rather than getting frustrated later. Any other questions? Okay. So again, I'll stop the sharing unless there's other questions. I'll be glad to answer them if you got them. Okay. And if I haven't, we're down to 5 people now. Okay. So it's okay to go on and close it. All right, take care, folks. And I should have mentioned this earlier. One of my students in yesterday's classes had tested positive for COVID. It's out there, folks. Be careful. Be safe. Don't assume it's over with. It's not. No matter who says we're rounding a corner, we're still in the thick of it. Okay? So be safe. Be careful. Take care. We'll see you Thursday. Okay? Bye-bye.